Now, like I said, if we look at this, the start of the exam, we have the formula book at the start, okay? So we'll go back to the formula book as needed. I'll show you where the formulas are. So let's have a look at question 1. Now, step-down transformer. So, who can tell me what step-down transformer means? Reduce the voltage, yeah. Has an input voltage of 250 and has an output voltage of 20. So, V1, what does that equal? 250. V2? 20. Okay. The primary winding is 850 turns. Now look, this question is for babies. He wants N2. Now we all remember the formula. It's V1 over V2 equals N1 over N2. But it's possibly in the formula book too. Let's see. Now maybe not. Oh, I can't see it. But anyways, you don't need to know this one. It's a simple one. Okay, so we have of course, write down the formula first. V1 over V2 equals N1 over N2. So you have 250 over 20 equals V1 over V2 equals N1 over N2. So I can cancel that with that. I can bring the 25 from here over to here. So let's see, it's 32, 35 times. I'm assuming 25 goes into 850 35 times. Please check. 34, thank you. So bring the N2 up here and the 2 up there, so we get 68 is N2. Yeah? Cool. That's part 1. We have 2 marks. 2% down, 98 to go. Now, if the current flowing in the second circuit is 6.4 amps, determine the power. So what's the formula for power? IV. 6.4 times the voltage. What's the voltage? 20. Is that right?
Why did we do 20?
Because it's flowing, he says, in the secondary circuit, not the primary. So we have, 4 down, 96 to go. Right, so, part 1. We have a mass of 1.4 kg, 1.45 kg. It hangs at the end of a spring, and it makes the spring extend by 92.5 millimeters. So, makes the spring extend. So the delta x, the extension is 0.00925. Is that right? 1, 2. I have too many zeros, don't I? Yes, I do. Sorry. 92 millimeters, what's that, about 9 centimeters. Sorry, so it should be like this, 925. Is that right now? Yeah, okay, 0.0925. Right, now, this one here that I do know there's actually the formulas in the formula book for this one. So if you swing back to page, top of page 4, I believe. No, that's not it, is it?
Page 3.
Page 3, sorry, is it page 3?
Which one?
We could use that, but in fact there's a better one. No, yeah, no, sorry, I was right the first time. Top of page 4. Look at the top of page 4 and go about 1, 2, 3, 4, 5 lines from the top. See, for a mass on a spring. Yes?
Yep.
Yeah.
So what do we have?
We have mass
Yeah,
and
on a spring.
Yeah.
So let's write in our formula to get us started. Okay. Now what is he looking for? Sorry, let me see.
Constant. Constant.
He's looking for the K.
but we don't have T.
No, actually, I've gone too fast into the question. The spring, it's not bouncing yet, it's just hanging, okay? So, sorry, that's the second part. My mistake. For the first part, this is just hanging here, and what's happening here? It's just pulling up, yeah. Now, it's balanced. So what happens here? It's not moving, so what happens here?
Equal.
Equilibrium, yeah, it's equal. So what's this downforce here? What's that called?
The gravity.
The weight, yeah? Yeah. What's the formula for that?
1.45 multiplied by
Yeah.
20.
Okay, so that is the weight. Now what's pulling it up?
Reaction.
Not the word I'm looking for. The spring. And what's the name of the force in the spring called? What's the name of the law? Hooke's law. Do you remember this? So the formula for Hooke's law, what does it equal? It's, yeah, K delta X. Now we know the delta X, yes? And this should equal this, right? So we can get the K. So we have K delta X, that's the up force, that should equal the down force. So the K will just equal the down force divided by the delta X. Can you hit that on the calculator carefully, please? Yes. Dude, I'm so tired of you sleeping in my class.
153.60.
What is it?
153.60.
15. Yeah.
153.62.
So we'll say 153.6 then. Okay, are you ready for the next part of this? Okay. Now, in the next part, he says it's pulled down and then it vibrates with simple harmonic motion. Oh, by the way, that Hooke's law, if you're looking for Hooke's law, that one is on page, let's see where it is. That one is on the middle of page 2. Now for the next part, we do need the formula at the top of page 4. Because what's happening now is he pulls the weight, the mass down some more, and it starts to do this, look. He pulls it down, and lets go, and it starts to move like this. So he says now, the mass is pulled down a further 20.5 millimeters and released so that it vibrates with simple harmonic motion. Determine the period of this motion. So if you go to the formulas for simple harmonic motion on the top of page 4, you see the formula is, he wants the T. T equals 2 pi root m over k. We want this one. So, what's the m here? And what's the k? So please calculate this.
T as a period.
Periodic time, yeah. Now, does he ask for the time or the frequency, actually? Yeah, okay, the time. And if he asks for the frequency, what will we do? 1 over the time. Yep. Okay. And now part 3, determine the maximum acceleration. Now again, if you go back to the top of page 4, which formula do you think we use? No, on the top of page 4? It's actually at the very top of page 4. A equals minus omega squared x. Now, we have the x. What's the x here? He says it in the question. What did he say it is? 20.5 millimeters. 0.025. But we don't have the omega. Does anybody remember what the omega is? And the formula is not here. So I'll put that in blue. Does anyone remember it? It's actually pretty simple. It's 2 pi over t. That's it. Which I do not believe is in this formula book. No. Oh, it is actually. If you look at the bottom of page 3. See at the bottom of page 3?
Yeah.
So it is in the book. So it's 2 pi all over t squared. Okay. Please calculate on your calculator this. What is it? 0.258? Thank you. Okay. Right, that is question 1 and 2. I find it quite reassuring for you and me that we've done 2 section A questions. I don't think there's any reason why you should not get full marks on these 2 so far. And that is already 2, 4, 6, 8, 11%. 11%. So you're already 1/4 of the way towards passing. Good news so far. Okay. Now part 3. Or question A3. So here, light of a wavelength 350 nanometers is basically fired at a clean metal surface, and out comes your photoelectrons, your photons, with a maximum velocity of 7.8 times 10 to the 5 meters per second. Calculate the Broglie wavelength for this. Now this might not be in the formula book. It wasn't last year, but they changed it slightly. Let's see if it is in this year. It is. You'd want to look under. It is.
Yeah.
What page?
Physics.
Huh?
Page 5, modern physics. The Broglie.
Yeah.
Awesome. Awesome. Guys, seriously, you're not even thinking now. It says calculated. No, really. What did it say to do? Calculated the Broglie wavelength. What did you do? You went to the formula book. You found a formula called
H over mv.
de Broglie, and the formula is the wavelength equals h over mv. Now the h is Planck's constant, which is, what's it, 6.63, is it? Where is it now? 6.63, yeah.
That's the formula book.
What's the mass? Well, it's electron, isn't it?
Yeah.
So it's 9.11 times 10 to the minus 31. And then the velocity is, he gives it?
7.8 multiplied by 10 to the power 5.
Okay. Multiply 7.8, multiply 10 to the 5. Now, hang on. In fairness, this was a particularly easy year. I will work backwards to the more difficult one. So don't get overconfident.
No, I'm not overconfident, just feeling happy that
But
gravy,
it can go well for you. Maybe. Yep. Can you calculate this, please, on your calculator? Come on, please. Yeah, that 9.11, 10 to the minus 31, yeah. So, when you hit that in, what do you get?
9.23 times 10.
Right, hang on. 9.23? 9.233? 9, yep.
10 minus
10 minus. Now, hang on, what's micro is 6 and nano is 9, isn't it? So this will equal, if you want to write it like this, it's 9.33 times 10 to the minus 1 times 10 to the minus 9. That's nano, so it's actually 0.933 nanometers. Yeah, okay. Not necessary. You could have stopped. It's perfectly fine to stop here. If you do stop here, of course, make sure you write in your units, meters here. Okay. Now, the next part is calculate the work function, and I saw the formula there. Which formula do we need? Well, it's again under modern physics, and it's this one. HF equals work function plus kinetic energy. And this is the frequency of the photon that's, hey, look up here. This HF, the F is the frequency of the photon that's released. Kinetic energy is the kinetic energy of the photon. And the phi here, the symbol here, is the work function, the energy required to free the photon. Okay? Sorry. Yeah, this is, if I draw it here, this is the photon coming in. No, sorry, or electron. I'm getting confused now.
Electron coming in.
I've been saying this backwards. This is the, this is the photon coming in, and the electron is what comes out. Now, he calls, I think this is unfortunate vocabulary, he calls the thing that comes out the photoelectron. Do you see that? In fact, I would much prefer if you just called it the electron. Okay? It's not, a photoelectron isn't something fancy, it's just an electron, okay? So if it helps you, just delete the word photo in photoelectron. Okay? So it's the photon that goes in and the electron that comes out. So, what's Planck's constant? 10 to the minus 34, isn't it?
Yeah.
And I want this, so I'll bring this to the left, minus the kinetic energy, which is a half m, and what's the m here? Mass of an electron.
9.11 of 10 to the power minus 31.
Thank you. Minus 31. A half m v squared, and he gives us the v also, doesn't he?
Yeah, V is...
Yeah, there it is. 7.8 times 10 to the 5 squared. Okay, that is the work function. Well, equals this. So please calculate this. Thank you. Go ahead. Is that calculating? Yep. Yep, this one is on the book. It's on page 5 in the middle. Huh? Photoelectric effect, yes. Yes. Huh? Oh, sorry. I didn't write in my F, thank you. We were asked to calculate the... Oh, no, we haven't got the F yet, sorry. Wait. I left out the F here. Here. So, yeah, you were saying there what formula would get us the F? V equals F lambda. So what does F equal? F is V over lambda. V here is given, and lambda is given. So it's 7.8 times 10 to the 5. I'm sorry you can't see this, of course. That's a 5. Over lambda, which is 9.33 times 10 to the minus 10. That's my F, which I can write in here now as soon as you get it for me. Let me make a bit more space. Minus, I don't even know what this is. Minus 10. Ugly. Right, do you have that F for me? Get rid of this.
8.36.
Whoa, slow down there. Have to make some space to write this F in. Yeah, hold your horses. Right, what's the F there?
8.36.
Yep.
Minus 10, 14.
10,
14.
14. Right, I'll squeeze this in here. 8.36. Sorry, this is so ugly. Times 10 to the 14. I'm so sorry about how ugly this is. Let me rewrite it. 6.63, 10 to the minus 34, 8.36 times 10 to the 14 minus a half, 9.11 times 10 to the minus 31. Oh, I'm out of space. 7.8, 10 to the 5 squared. Right. Of course, when you're doing this in the exam, you don't need to write as big as me. You can see that took up like 3 lines in the copybook. Yes?
The formula is HF equals
Work function plus kinetic energy.
The frequency is 10 to the power.
8.36 times 10 to the 14. Okay, do you have that?
2.77.
Thank you. What is it? 2.77
10 minus 10.
times
10 minus 9.
Oh, that looks so ugly. Right, the last part now is calculate the threshold frequency. Does anybody remember that? Listen carefully. The threshold is when the electron just about leaves the metal surface. So what would the velocity be? Zero. So it's in fact the same formula except for this kinetic energy part is 0. So the work function would just equal 6.63, 10 to the minus 34.
8.36, 10 to 14.
There we go.
No times.
5.54
What's it?
times 10 minus 9.
10 to the
Minus 90.
minus 90. Now, that's actually the amount of energy required to just about free it. That's the energy, the work function. But he doesn't want the energy. He doesn't want the threshold energy. What does he want? Frequency. So what formula do we use? Yeah, very good. E equals HF. This equals HF. So all I have to do is divide this number by my Planck's constant, which is 6.63
Times 2 to the power minus 34.
31 or 34, isn't it?
Which would be 8.36 to
Yeah.
the power 14.
It's just the
It's just the same.
8.36, yeah, because I cancelled out. I should put in my units. This here is hertz. This here is joules. Yeah, I wrote that in. And nanometers, okay. Yeah, pretty easy. Now number 4 is something we haven't done yet. Well, we've done it, but not in too much detail. I have left all the experiments until the end. And there's 15 experiments you need to have learned for the exam. But I feel like it'd probably be better if we actually do this nearer to the exam, you know, to learn off the experiments. But there's only 15 of them. 4 of them you will know because you did 4 of them in class, so there's 11 you have to learn. Okay? And the 11, one of them is number 4. So I'll just give you a very quick sketch of what's happening in number 4. In number 4, he says, the air in a cylinder pipe is the pipe is 1.25 meters long. So I'll just draw something like this. And closed at one end is made to vibrate at fundamental frequency. So it's closed here. Is it closed? Yeah, of course it is. Determine the vibration of the air, neglecting the end correction of the pipe. Take the velocity of sound in air to be 340. Oh, sorry. No. He's saying that this will vibrate. Okay? So you're picturing a wave inside this. Okay? Now, there's a few ways you can imagine the wave, sound wave inside this, the wave inside it. So one way to imagine it would be the waves like this. Okay? Second way to imagine it is maybe the wave is like this and it continues out like that. The last way to imagine it is it goes from the center up to the top, and then it goes back down on the outside. So basically it's hard to see, but I've done 3 possibilities. The red possibility is all the wave is inside of it, the blue one is half the wave is inside of it, and the green one is a quarter of the wave is inside it. Which one do you think it is? Well, let me just put it this way. Of the 3, which one do you think will make it vibrate the most? Now, why do you think that?
Because too much time hitting.
Now, think about it. With the red one, when the energy hits the top, it's at the same time as the energy hits the bottom. So they kind of cancel each other, right? Now, what about the blue one? Yeah, it hits it up here. But the one that does the most is actually the green one. Because the maximum point, the concentration of the energy in the wave hits it at the end. And this is the one that would cause it to vibrate the most. It's a bit like if actually here, just right here. Like your possibilities are the wave is inside it and it's going up and down. But at the same time as it goes up, the other half also goes down. So it kind of, it doesn't really do, it vibrates, but not as much as the other ones. Because with the green one, if the wave is only 1/4 inside of it, so it goes like this, okay, it means you have all the energy hitting it here, so it'll go like this. So, yes, you want the maximum force, but don't forget about turning force as well. Remember turning force? So what's turning force? F times D. The red one is a no-no because the up cancels the down. The blue one is possible, but the green one is better because if we look at the blue one, here's the distance, yes? And if we look at the green one, here's the distance. Now I know this seems very confusing, and that's because I haven't talk too much about this experiment. But the only thing you need to remember about this experiment is, listen carefully, 1/4 of the wave is inside the pipe. Okay? 1/4 of the wave. Alright, so with that in mind, it means that, what's the wavelength? 1/4. So if the pipe is 1.25 long, then the wavelength, what would that equal? It'd be 4 of these, which is 5 meters. Isn't it? Yes? Now, he also gives me the V. What's the V here? He says it, what is it?
340.
340. And what does he want? What does he want?
The cases.
Frequency. So what's the formula? V equals F lambda. So V equals F, sorry, not V. F equals V over lambda. So F equals V over lambda. What's that going to be now? 6, what's it? Oh yeah, 68. 68 hertz. So that means this pipe vibrates at what frequency? 68 hertz. Okay, so in fact, once you know this piece of information, then the question is easy. But like I said, we'll look at the experiments in more detail next week, okay? I just want to have a look at one exam, and then we'll look at all, no, sorry, not next week. When you submit your final lab report, then we'll look at the experiments, all of them for the course. But I don't want to spend too much time on them, because when I look at this whole exam, the experiments you're supposed to learn only came up in one question, this question, and how many marks? 3 marks. So it just seems to me to be a waste of study time to worry too much about learning off these experiments when they'll only get you 3 marks. We will learn them off. Huh?
Is it a trend in the exam paper?
It is a trend in the exam paper. That is the reason why I am leaving the experiments until the very end. So that it's very recent when we've done them. So you can remember them easily when you go into the exam. Fair enough? Okay. And that's it for 4. Now on to 5. The planet Venus moves in a circular orbit of radius that. Around the Sun. The period of revolution is this. So yes, circular motion. Calculate the velocity. So in fact, if you go to the circular motion formulas, you can see for yourself. Which page is it on for you? It's
3.
page 3, yeah. Yeah. I think
Omega is equals to V over R.
first we should get the omega, yeah, because we need the omega in the formula. So if you look at the very bottom of page 3, you have T equals 2 pi over omega. So that means omega equals 2 pi over T, which equals 2 pi over 1.94 times 10 to the 7, which equals, please calculate. What is it?
3.24 times 10 to the 7.
Radians a second is the unit. Okay, now that we have our omega, we can now get the V, because he says omega equals V over R, so therefore V equals omega R, so therefore V equals omega times R, which is 1.94 times 10 to the 7.
No, 1.
Oh, sorry, 1.08 times 10 to the 11. Okay. Please calculate. So it's going to be, what's it going to be, like 6, oh sorry, what is it?
3492.
Say, if I'm doing it too fast.
34992.
34992. Cool. Right, next is calculate the mass of the sun. Now, I think we should use, we definitely need to use Newton's F equals G/mm over R squared. Yeah, so look here. I'm going to go to a new page just to make more space. So here's the sun, that's big M, and here's our planet, that's small m. Now, what does Newton say? F equals G/mm over R squared, and there's my planet going around. And also, what does Newton say? F equals ma. So if I make these equal, I get G/mm over R squared equals ma. Go. Now, do we know big G?
Yes.
Do we know the radius?
Yes.
Yeah. Do we know mass? No. That's what we want. And do we know A? No. So let's change A. Look at your circular formulas. Which formula should we use for A at the bottom of page 3? Yeah, what is it? Yeah, I should say A equals V squared over R. Now what happens to the R power? That cancels that. Let me bring the R up here. And let me bring the G down here. And I've just made up a new formula. M, the mass, equals V squared R over G, which equals 34992 over 6.67 times 10 to the minus 11, isn't it? No, you're thinking of Planck's constant there, I think. And then that's a square, and then times the radius, which is 1.08 times 10 to the 11. And there we go, that's our mass. Please calculate. G is that, isn't it? Yeah. Yep. Times 10, 30. Pretty big, but it should be. It's the sun. No, it doesn't give it as a constant. Right. Next one, so. Number 6. A stationary radioactive nucleus with nucleon number 220. What does that mean?
Stable.
No, sorry, the 220, what is that? What's the, maybe you've done this in chemistry, what's the nucleon number?
The proton numbers?
I think it's actually the protons and the neutrons. It's the nucleus number. It emits an alpha particle with that velocity. So, basically the first question is, how many nucleons do you have left after the decay? So look here, we start off with an atom. How many protons and neutrons? 220. And then an alpha is fired out. What is an alpha, by the way? Not hydrogen, helium. How many protons, how many neutrons? 2. 2 protons, 2 neutrons. So how many protons and neutrons together? 4. How many did I have here to begin with? 220. So if an alpha is fired out,
261.
so provided that you're smart enough to do this, you should get the right answer. Now look at the marks. How many marks for that?
It says both of these.
One.
Yeah, that's just the name they call this. They call this the daughter.
Now she's a daughter.
Yes.
She was a mother.
No. I realise it seems like a silly name. If anything, this should be called the daughter because this came out of this.
Yes.
And it's smaller.
Yes.
So I don't think it's a accurate description. If anything, this should be called the mother nucleus and this should be the daughter nucleus. But oh well. Physicists aren't good at naming things, I guess. Right. That's A part 1. And now part 2. Use conservation of momentum to calculate the velocity of the daughter. So in other words, we want the velocity of this experiment. Before the decay, what's the velocity of...
1.63 multiplied by 10 to the power minus 10 to
No, before. It's 0. And then after, that's the after, it shoots out. So look, it goes like this. Before, here is the nucleus, there's 220 protons and neutrons and everybody's happy. And then what happens is this fires out. Helium 4. And then this will move backwards this way. A lot like a gun, you know. So, what is the momentum before? 0. It's not moving. 0. Now, I'll call this velocity P. I don't know it. And this one I do know. What is it? 10 to the 7. Okay. Now, what's the conservation of momentum?
And V
Yeah. Well, give it to me in words. The momentum before
equals
equals momentum after. What's the momentum before? 0.
0.
Equals the momentum after. Now, what's the mass of this? And it's okay just to use the number of protons and neutrons, it's fine. So its mass is 216. And what's the velocity? P. No, this one.
This is daughter or the mother?
This is the daughter.
So we have for the daughter. No, we for
No, we don't.
we have for the other.
Wait, don't confuse me. No, the alpha is this one. And he wants the daughter one, which is this one. He wants this one. You don't know this one. You know this one. So the momentum of that is that. And what's the momentum of this one? What's the mass?
1.4.
First the mass. What's the mass? 4. And the velocity?
1.63 multiplied.
Now, if you want to be formal about it, the mass isn't 216. What actually is the mass? It's 216 times the mass of a proton or neutron or whatever. But in fact, it doesn't matter because if I write the mass here and if I write the mass here, what happens? Cancel. So for these, I'll give you a little hint. In fact, for these nuclear problems, sometimes when you need to use the conservation of momentum, the mass cancels always. So you can just write down the, the mass number, which is 216 and 4. Is that okay?
Yep.
Are you sure?
Yes.
Give me the P, so calculate it.
3.019.
3 point
0.08 times 10
power 5. Quite fast, so.
That is negative.
Yes. Well, does he say velocity or speed? Velocity. So minus to the left. All right. You are writing this down, aren't you? But what happens if when I save this video, it crashes and doesn't save?
You were supposed to tell us that in the beginning.
No, because I don't know if that will happen. What happens if God sends a bolt of lightning down to my laptop and fries it? I I don't know that's going to happen.
That would be too specific.
It would be. But maybe I'm being punished. Maybe I'm being punished for being too kind to you. Yeah, maybe. Let's hope. Actually, I'll tell you what, if it breaks, we know we're being punished, though. Yeah? Okay. Number 7 now. Yeah, only 3 marks, but not too difficult 3. Right. You've done ionization in chemistry. So the energy level is minus 24.6 electron volts. What does ionize mean?
The energy
To free it. And I give you a simple little definition. Something is free, like our example with, remember the threshold frequency. What was the kinetic energy of the free particle when it's just about free? 0. So I need this energy to be 0. And what's the energy now? Minus 24.6 eV. So the energy that's required to free it is, have a guess?
plus
24.6 eV. But he wants it in joules. Now, you've done electron volt in chemistry? I know we did it. Do you do it in chemistry too? Anyways, it doesn't matter. If you look at the start of the book, look at page 2, you can see the electron volt is 1.6 times 10 to the minus 19 joules.
2.
Page 2, electron volt, yeah.
1.6 multiplied by 10 to the power 19 minus 19
Yeah.
joules.
So just multiply those 2, please. Hey, this question's only 1 mark.
Oh, I just realized I broke the screen of my tablet.
How did you do that?
I don't know, it was in the back.
Did a lightning bolt hit it?
Maybe.
Maybe. Can somebody please calculate this?
3.936.
3,936
Times 10 by minus
minus 8?
8.
18 joules. Easy peasy lemon squeezy. Right, number 2. Determine the frequency of the photon emitted when an electron returns from 0 energy level directly to the ground state. So in other words, what's the frequency you get here with the photon? So determine the frequency of the photon emitted when an electron returns from the 0 energy level directly to the ground state. So it goes from 0 energy to this ground state. So you have the energy basically. I mean, we've seen one like this before, haven't we? We have the energy and you want the frequency. So what formula do you use?
EHF.
Yeah, it's just E equals HF again. So he wants the F. F equals E
Divided by H.
31 or 34. I was
21. 34.
Thank you. Okay, what is it?
5.937.
Thank you, what is it?
5.937. Times 10 by
10,
by 15.
15. Unit? Now, there's only one left in section A, but it's big enough. It's the biggest one. Yeah. So, what I'll do is, let me pause this video Now it's recording.
By the way,
Now it's recording.
look, he's
Thank you, it's very kind of you. Please put that there and sit down, thank you. All right.
snitch. I'm not a snitch, I'm just a law-abiding snitch. Law-abiding snitch.
Come on, snitch, we're trying to continue here.
Oh!
Hey, yeah, who's going to say that? Hey, you just been served. Right, 8. Last part of section A, and it's quite a big question, so look carefully at it, please. Look at number 8. What you have is a uniform shop sign of mass 8.5 and width 0.6 hangs as shown from a bar 1 meter long. Basically all the lengths are there in the diagram. So if I try and draw that here, there's my wall, and here is my wire. So of course there is a tension, T, in the wire. It's like a force here. And of course there's gravity. But what you have to be really careful about is, and I actually, when the first time I saw this question, I forgot this, the gravity acts right in the center of the shop sign. So it's not here at the end, but here. Got any Coke?
Okay.
No, it's okay. I actually wanted Coke. It's all right. Just stop saying that. Now, the weight is 8.5 G. Okay. That's right, isn't it? Now let me put in the distances.
It's kilogram, 8.5.
Yeah, but this is the weight. That G is not grams, it's gravity. No, I'm multiplying it by 9. Oh, never mind. Right. Now, let me put in the lengths. So, right, let's go with green. So how long is this piece here? That is 0.8 meters. Focus, people. Omar, you troublemaker. Focus. Now, how big is here to here? Hey, how big is here to here?
1 meter.
No. 0.7. Because the weight acts in the middle of the sign. So it acts 0.3 from the end. So then, how much is this piece here?
0.3.
Yeah, 0.3. Now, I have to break up my forces. So, this T I'll break up into a force this way, and I'll break up into a force this way. Now, if I call this angle here alpha, this will be T sine alpha, and this one here, T cos alpha. Okay? Now, let's not forget also that he says, I believe there's a little hinge here. Yeah, there's going to be a little hinge here. You know what a hinge is? Like on the door hinge. Hinge, H-I, okay, hang on. hinge. So, we have to remember that, please people, we also have force here at the other end of the string, and the hinge stops the sign from falling down, so there's an upward force here which I call Y, and also there's a reaction. You know when you push against the wall, what happens?
The wall pushes it.
Push it back, so there's a reaction this way which I call X. All very complicated diagram, as you can see. So I'll just give you a moment just to look over that. Let's see, the first part is he wants the tension in the wire, then he wants the horizontal force, which is the X, and then he wants the vertical force, which is the Y. To me, you just have to do all of them together. I don't see any point in him breaking them down like this. So, what we do is we write down our equations. Come on. Oh, by the way, I should also write down here, what does cos alpha equal? Cos alpha equals, what's the cos alpha? Adjacent hypotenuse. Now I need to use Pythagoras to get this, but it's going to be just give me a calculator, it'll be easier. So the hypotenuse for this triangle is square root 1 plus 0.8 squared. The hypotenuse is 1.28. Okay, so that's cos alpha. And then sine alpha equals 0.8 over 1.28. Okay. Actually, I'm not, I shouldn't have put this, I know there is a t here, but I don't really care about this t here. The reason I don't care about this t here, anybody can tell me why? I don't care about this t because it's stuck here, like with glue. It will never come out, okay? So you don't care about those ones, I'll just care about the other ones. Alright, now time for the fun part, writing down all our equations. So, what is the up forces in this diagram?
Y.
T sine alpha, and what else below? Y. And what's the down forces?
X.
8.5, 9.81. Okay. Now, what's the left forces? T cos alpha. And that should equal the right forces if it's balanced. What's the right forces? X. Quick look here. How many unknowns are there? How many things do I not know? What do I not know? Do I know cos alpha? Yes. Do I know sine alpha?
Yes.
Do I know X?
No.
Do I know Y?
No.
Do I know T? And what does he, no, I don't know T. And what does he want? X, Y, T. So I have 3 unknowns. How many equations should I have?
3.
So I'm missing one. Who can tell me where I get number 3 from? Equation number 3. I've used up force equals down force, left force equals right force, and is this sign rotating? No. So the turning force is 0. So the clockwise turning force equals anti-clockwise. Very good, people. Now, what should we take as the turning point? Here, the hinge. So, we have how many forces causing it to turn here? Will this red one cause it to turn?
No.
No, why not below? Because it goes through the turning point. Very good. Will this one cause it to turn?
Yes.
No. Hang on, teamwork. No fighting. Teamwork. Yeah? Will this cause it to turn?
Yes.
Yes. Will this one?
Yes.
Yes. This one?
No.
No. This one?
No.
This one?
Yes.
No, because it goes through the centre also.
Oh, yeah, see when it says it goes up? You mean the
This-
sign goes up?
Huh?
The sign.
Which will cause it to?
Yeah. Will this cause it to, no, this way. Will this cause it to turn clockwise or anti-clockwise?
Anti-clockwise.
Anti-clockwise. And this one?
Clockwise.
Clockwise. So what did I say the rule is?
Anti-clockwise.
Yeah. Now who remembers turning force? It's force multiply distance. What's the distance here? 1. What's the force? No, what's the force? T sine alpha. That should equal this one. What's the distance?
0.7.
And what's the force? There it is there. Now look how nice that is. Do we know sine alpha? There's equation 1, 2 and 3. Do we know sine alpha? Yes, there it is at the top. So now I can know my t. T equals 8.5, 9.81 over sine alpha, which is 0.8 over 1.28. Yeah.
Do we have hypotenuse over here?
We used Pythagoras to find it. He's not in the diagram. 133.4 newtons. Perfect. Now that I know the T, what should I get next?
False.
Yeah, which one? The X or the Y? Either, but I think the X is easier because I can just put that in here for T, yeah? So I get X equals T cos alpha. 104.2 newtons. And last is the Y, so I can get that here. So I have that minus that. Okay, 8.5 times 9.81 minus T times sine alpha. What's sine alpha? Or was did you write it down? 0.8 over 1.28. Okay. Oh, that's a very nice number. 0.01? Yeah. Okay. That is for great. That is part 3. That is part 2. And that is part 1. So what was the difficult part in this question?
Trying to locate all of this.
Yep, trying to draw all the forces on the diagram. Quite difficult. So I recommend you practice a couple of these when we look at the past papers, okay? This was the one that caused everybody in September. 100% of the class in September. 100% of them had trouble with this one. 100%. Now I'll start section B. I'll get a. No, wait a second. First, let me see if this will save properly. Wait.